different trophic levels. Sometimes you can measure diet directly by observations. You can also measure diet by examining gut contents. In this case, there's actually quantitative estimates for these, and you can, for fish especially, you can get gut contents very easily because you can make fish vomit, and you can just count what's in their guts fairly easily. You can make observations on things like seals. But when you get lower down this trophic, in these trophic levels down here, we're talking about things like squid and shrimp and scallops and stuff like that. There's some observational data that can be used to make general predictions of what the relative strengths are.
Maximum number of links is n squared minus n.
Okay. There we go. Thank you.
Also known as n choose 2 times 2.
All right. See, this goes up. Basically, the point I was trying to make badly was this goes up like the square of species richness. Whereas, if you think about the number of links, if connectance was to remain constant with species richness, then the number of links per species would have to go up like the square too. So, anyway, I want to tackle this question of, so this is the idea, getting back to this whole problem of general uncertainty in trying to predict what's going on. So this is a different marine food web. This is off the Benguela current system off the coast of South Africa. There were spots that they, in this case, would cull the South African fur seal to increase the catch of a whole bunch of fish that were part of the fishery. So what Peter Yodzis did in this case was they took quantitative estimates of all these, but there's error in these quantitative estimates, as it's not too surprising. And basically, he looked at, if you sample from that error amongst all the different interaction strengths, so basically how much of each species each of the other, and then try to predict what the net effect of each reduction in population abundance of the fur seal does to the species, then you get an extraordinary amount of spread. All four of these panels here represent different types of assumptions. I don't remember the exact details. In the upper left, this is just a model with type 1 functional responses. Then you start adding different types of type 2 functional responses and type 3 functional responses where species respond at varying densities. The important thing is that on average, and the median result in this case is that actually reducing harp seals on average leads to a dramatic, or not dramatic, but a reduction in the yield of all fish. But, which is this dashed line here, which is 0 change. But there's an enormous amount of spread. So even if you found a positive effect on average, it would be very difficult to estimate what the net result is. These are all, once again, based on equilibrium solutions to this. So if you basically change the abundance of the seal and then let the system equilibrate, when you get these highly complicated systems, it takes a long time for these systems to equilibrate. So there might be the overall effect on fishing might change through time. And what this is the really, well, there can be a lot of depressing things, I think, in food web stuff, but when you start really considering broad food web effects, it's really, really difficult to make quantitative predictions about individual members of those species within these food webs. At this point, we haven't made the progress we need. So this sort of general idea that there's uncertainty in quantitative predictions coming out of the quantitative webs has led ecologists to try to make more kind of gross predictions about food webs. And I'm going to talk about some of those, but first I want to talk about looking at this idea of trophic level and how we assign trophic levels. So we go from a food chain model to a model with omnivory. I'm going to use this to illustrate how we talk about food chain length. So all the organisms, in this case, we know what their food, what their trophic level is. 1, 2, 3. What's the trophic level here? Well, there are different ways of doing it. One technique is to look at the maximum chain length. So in this case, the maximum chain length would be the longest pathway from a basal resource to an identified organism. So this consumer's maximum chain length, these are all chain lengths that go up on food connections. You can't go back down in these cases. So you go up to a consumer, and this is a 2 still. So omnivory hasn't changed the trophic position. In this case, the maximum chain length would be 3, because the maximum length you go boop, boop, boop. So 3 would be the maximum chain length. But that ignores the fact that this predator is getting some of its food from the resource. So we're talking about where its energy is coming from. Some is coming from the consumer, so it's the second food chain, trophic level, and some is coming from its resource. So another way to do this is the average chain length. So this would be a 3 is one chain, and the other chain is this way, which is a 2. So this guy would be trophic level 2.5. Now, if we want to think about where energy is going and how many energy transformations, this is a dramatic improvement. And to see why this is a dramatic improvement, let's look at this food chain. So 1, 2, 3, 4, 5, 6. This could have a trophic level of 6 for that top guy. And as you get more and more species with some amount of omnivory, you get really, really long food chain lengths when you take into consideration these maximum chain lengths. So in the absence of better information, the average chain length is the best way to estimate food chain length. And these are in these qualitative food webs, where we don't have quantitative estimates. When we do have relative strengths, we know sort of the proportion of the diets that go into these different ones. So this one gets 100% of its diet going this way. And let's say this one has 60% of its diet coming this way, and 40% of its diet coming this way. Then we can make a quantitative estimate of food chain by weighting the length of it, doing a weighted average of all these different senses. So 60% times 3 and 40% times 2, which is going to give you a food chain length that's higher than 2.5. It's going to be, I don't know, it's going to be approximately 2.6 or 2.7. It's going to be greater than 2.5. So that's the best, and that's really an accurate way of measuring food chain length in these kinds of systems. Once again, finding these quantitative estimates on large food chains like this is extraordinarily expensive to do, because you have to measure all the diets of all the different species and look at the relative abundance of different species within those diets. And so it becomes extraordinarily cost prohibitive. A way around this is to take advantage of the properties of certain stable isotopes. And you can, in a sense, by using these stable isotopes, you can directly measure these food chain lengths. So there are many different isotopes that are used in food chain studies. The two that are most prominent are nitrogen isotopes. So when nitrogen is taken up within an organism's tissues, some of it, and organisms excrete some nitrogen. So these are once again stable isotopes, so they're not radioactive. Organisms selectively excrete lighter nitrogen isotopes, so basically N13. So as you go up food chains, there's a predictable amount of change in the ratio of N13 to N14 as you go up the food chain. So you, on average, you're getting, the ratios are going from, you get higher ratios. As you go up food chain. So basically, each transformation of nitrogen within a food chain, you have a set amount of change, which is on the order of this delta, sort of on the order of about 5 individual, 4 to 5 orders of magnitude change here. We also have on the bottom of this graph, so these are just measured ratios of carbon and nitrogen. But this is 14 and 15. This is carbon 13 and carbon 12. So carbon is a good tracker in this case. Carbon fractionation only occurs during photosynthesis. So different types of plants will have different stable carbon ratios. We have prominent differentiation between C3 and C4 plants.